Hi, everyone. Welcome to the talk. The agenda for today is to describe how we use Julia to build a new kind of cloud-native relational database management system that supports knowledge graph use cases. I will explain some of this as we go. I hope the content in this talk will be interesting to anyone who knows Julia, but it will make the most sense if you know something about databases, cloud computing, compilers, and knowledge graphs. So briefly, what is a knowledge graph? According to Wikipedia, a knowledge graph is a knowledge base that uses graph-structured data model to integrate knowledge and data at scale. Okay, it's a way of representing knowledge and data that humans and machines can understand. And I believe that future systems will be built with knowledge graphs as a foundation where each component or service in that system will either be learned via machine learning or it will be declared and executed via a sophisticated reasoning engine. You know, think SQL or Excel spreadsheets on steroids. And only as a last resort will we have to instruct the computer step by step how to perform a certain task. So how do you build a knowledge graph management system? Well, first you have to answer two questions. The first question is, how do we represent graphs? And the second question is, how do we represent knowledge? So how should we represent graphs? Our answer is with relations. And if you've worked with graphs before, you know there are different ways of representing them. But a very common way is to represent the edges in a graph with an edge relation that maps source node to destination node if the graph is directed, or just connects two nodes if the graph is undirected. And so here's a quick example of that. Of course, relations are a universal abstraction. You saw just now how we represent a graph with a binary relation. We can also represent a hypergraph where you have edges between 3 or more nodes as an n-array relation. Functions are also represented via graphs, tensors, sets, bags, and so on. And the cool thing about the relational paradigm is that you can separate the abstraction from the implementation. Relations can be mapped to adjacency lists, to B trees, to hash maps, to a variety of data structures that might be more or less suited for a particular data set and particular payload. Second question is, how should we represent knowledge? And our answer to the second question is that you should represent knowledge with a relational language. And we've built a small and simple core relational language that supports one core type of structure, which is the relation. And relations can then be used to, can be specialized to represent other things like functions and tensors and graphs and so on. There are 3 language constructs in this core language. Identifiers, so how you name things, name variables and name relations, introduced via bindings. The second is abstraction, so anonymous relations, or the equivalent of a lambda in functional programming. And the third is application, which is like function application in a functional language. And there are 7 types of formula operators. The first 6 you know very well: conjunction, disjunction, implication, negation, the fixed point operator, which is recursion, and first order quantifiers, which you can use to build aggregations and reduce things, reduce relations, you know, sum across the rows of a relation. And the third type of operator is less well known, but it's a second order quantifiers, and lets us make statements like there exists a relation that satisfies the following properties, and is a really nice way to integrate solvers and optimizers into the language, because that's what you would use a solver, for example, to find a relation that satisfies a set of properties. And from this core language, we build on it to get tables and SQL for the business analyst community, likes to work with tables and SQL, tensors and linear algebra for the data science and ML community, graphs and navigational queries for the graph community, and then JSON and graphical, which are sort of preferred abstractions by the developer community. And we implement these abstractions as views on a common internal representation. And the key insight here is that the table, the tensor, the graph, the JSON abstractions are just views on graph normal form relational schema, or as it's sometimes called, a 6 normal form schema. A graph normal form relation is a key plus at most one other column, so it's irreducible. You can't break it down into components that you can reassemble with the relational language. It's just basically, it can't go any smaller. Most people have never heard of graph normal form and 6 normal form because they're not practical to implement in traditional SQL relational databases, because you end up with way too many relations, way too many tables, and then you end up with having to join them all back together, which is super expensive in the context of those types of database engines. So you might ask, can we have the abstractions and high performance? And I'm here to tell you that yes, we can, as long as we use a new generation of join algorithms, optimizers, and data structures to make that work. Okay, the rest of this talk is going to be about that. So our system is built with 3 design principles in mind. One is leverage. Let's just leverage what work that other people have done, in particular cloud computing. Let's leverage all that infrastructure, in particular the object storage systems that come with cloud computers, that in a sort of traditional database, the storage manager would take 70% of the code, whereas here we're gonna basically leverage AWS or Microsoft Azure or Google's investment in their respective object store systems. Okay. The other thing, of course, we're leveraging is modern languages and compilers, specifically Julia and LLVM. We're also building a system that is clever and strong. Most systems today that are built with performance and scalability in mind, they basically achieve that performance and scalability by throwing hardware at the problem. We want to go faster and be more scalable by avoiding work, not just doing the same units of work with many, many more workers. And we also pay attention to the constant factors, and we manage, we do latency hiding, manage latency hiding the right way in sort of the 7-layer deep memory hierarchies that exist today in terms of global storage, local storage, RAM, global RAM, socket RAM, NUMA node RAM, L3 cache, L2 cache, L1 cache, the registers. Anyways, managing that memory hierarchy is very important to us, and making sure that the constant factors are good, along with having strong support for automatic parallelization and specialization. And then finally, we aggressively simplify and consolidate the system. In fact, there are 5 core capabilities that we can compose elegantly in ways that cover a broad range of use cases. And the system today already does a lot, and it's less than 100,000 lines of code. It's hard to imagine that the core of the system is going to grow beyond 200,000 lines, even after we add the pieces that the few pieces that are missing. Okay, so let's talk about these 5 capabilities one at a time. The first is a query compiler that basically eliminates the interpretation overhead that you see in many database systems. Most database systems implement query evaluation via an interpreter. And in our system, we wanted to compile the query down to machine code and run it as if it was, written to be compiled. Okay, so a very brief example here. You see the select query. In our system, the select query will be optimized using a very sophisticated semantic query optimizer, and the resulting execution graph is then emitted as a Julia program, which we give to Julia, and Julia analyzes that and optimizes that further and emits LLVM IR, and then LLVM takes that and emits machine code that runs very efficiently. And in fact, this is the machine code that executes that SQL query there. Okay, we benchmarked this against best-in-class systems for doing business intelligence analytics. And as you can see here, we do quite well on this TPCH benchmark on a scale factor of 100, which is about 100 gigabytes of data. We do quite well relative to the best-in-class systems, and we do very, very well against popular systems like Spark, where, as you can see here, the closed source optimized version of Spark running on 16 cores takes more than 4 times the time that we run the same 22 queries on 1 core. Okay, so 16 cores run 4 times slower than we do, because systems like Spark don't pay attention to constant factors and interpretation overhead and so on. You can learn more about how we do this by taking a look at Jamie Brendan's JuliaCon 2018 talk, or Nathan Daly's JuliaCon 2019 talk. They explain in more detail how we do some of this query compilation and so on. All right, the next major building block is incremental maintenance. As the cliche goes, the only constant is change. And the goal of incremental maintenance is to minimize the cost of change. And ideally, if the thing that you're computing before the change doesn't change that much after the change, then you want the system not to do that much work. So in general, small changes in input don't most of the time lead to big changes in output. And if that is the case, we want to do a little bit of work to incrementally update the computation that we've already done. And that's really important for implementing things like integrity constraints, live programming, online learning, and a lot of other important components of a relational database and a knowledge graph management system. Okay, we treat incremental maintenance as just another compiler optimization. To illustrate this, consider the simplest of relational programs, a single hop exploration in a knowledge graph. Our compiler will rewrite it into a derivative with respect to changes in nodes and edges. Okay, so these are sort of the derivatives. And the compiler introduces counts for each tuple to capture changes, like is this piece of information supported more or less by the changes that are being made. And the counts and the derivatives efficiently maintain the query result as the knowledge graph changes. And we support incremental maintenance on any program you can write in our relational language, including those that involve aggregations and negation and existential quantification, recursion, and so on. It's really important to support the full language. Most database systems, if they support incremental maintenance, they support it on a fragment of the language. So like any other optimization, incremental maintenance comes with trade-offs because we need to remember previous results to use them in incremental maintenance. So effectively, we're trading off space and time. Ideally, we don't want the user to have to worry about these trade-offs, and users shouldn't need to know anything about incremental maintenance other than it just works. And Julia helps us with this because it makes it easier to gradually optimize the program as we learn more about how it's being used. So we start off by assuming that all inputs are static, unchanging, and optimize the program for sort of single use. But as transactions come in and start to update the inputs, we recompile the affected program fragments to their derivatives and then start keeping track of the counts in order to do efficient incremental maintenance. Okay. We also support incremental compilation, also known as incremental view adaptation or incremental metadata maintenance. I'm not going to talk about that today. Please check out Nathan's talk at this JuliaCon on Salsa.jl about how we do that and the vast ramifications of that. This Salsa work is based on work done by the Rust community, and the incremental maintenance work that I described earlier was based on work by Frank McSherry, who's built systems that do differential data flow and timely data flow. The next capability is immutable data structures. So let's talk about a key part of our performance story here, which is the data structures. In a busy database, you have multiple database versions being manipulated by many threads. And the question is, how can we design fast data structures for this? One possibility is shared immutable data structures, but these suffer from synchronization overhead, either in the form of mutexes or bus locks or so-called lock-free data structures. Another possibility is purely functional data structures, which don't require synchronization, but have a significant copying cost, typically logarithmic in n. We're using a hybrid approach here that gets us the best of both worlds, which we call MUTS, which is short for mutable until shared. In the MUTS discipline, data structures local to a thread are mutable and can be destructively updated, which avoids much of the overhead from copying data every time you need to update it. Data structures shared between threads are always immutable, which means that no locks are required and there is no cache coherence overhead. the root pointer uniquely identifies the state of the data structure, basically. So the MUTS discipline achieves isolation, the I in the ACID properties that you sometimes hear about being important for databases, which also, while also scaling to many cores. Okay? So we've been developing a library for efficient MUTS data structures, and I'll talk about two of these data structures briefly. The first is MUTS-Dict, the MUTS dictionary, which is our version of Julia's Dict or dictionary, and soon to be available as a community contribution. So we're going to put it out there for anyone to use who's interested in this kind of data structure. In addition to the usual Dict interface, the MUTS dictionary provides branch and mark immutable methods. The branch method returns a mutable copy of the dictionary in constant time. A thread can call a branch, make a sequence of modifications to the dictionary by calling setIndex, then call mark immutable before sharing it with other threads. And making an efficient MUTS dictionary took some careful data structure design. This table compares the asymptotics of Julia's dictionary to the MUTS dictionary. Both provide constant time lookups using getIndex. SetIndex runs slightly slower for the MUTS dictionary n to the 1/7, but this is much faster than lock time for small or medium-sized dictionaries that fit in memory. And the cost of setIndex gets cheaper the more changes you make to a version. An interesting footnote here is that the worst-case performance of setIndex for Julia's dictionary is linear time when a hash table resize is triggered. But the worst-case setIndex for a MUTS dictionary is only n to the 1/7, which makes it much better suited for applications where update latency matters. Now we get to the intended use cases, which is having multiple versions of the same dictionary coexisting at the same time and branching new versions. With Julia's dictionary, if you want to make a copy of a dictionary that won't reflect changes made by other threads, you need to do a deep copy, which takes linear time. With the MUTS dictionary, the branch operation takes constant time. We also provide an efficient setdiff to quickly iterate the differences between two versions of the dictionary. This runs in times that proportional to the number of changes in the two version, plus a little bit of overhead. So the MUTS dictionary is our go-to data structure for in-memory dictionaries. For durable storage and big data, we also have to have page data structures. And in this case, in our case, we've implemented a B epsilon tree in Julia using the blobs.jl package, a package that we also built and open sourced. If you're not familiar with page data structures, a B tree is optimized for disk storage, where each node in the tree is, for example, 64 kilobytes. It can be more or it can be less. And the branching factors are enormous. For example, a node might have 1,000 children. In a traditional B tree, a set index or an update operation would navigate to the tree to find the appropriate leaf node and update or insert the record there. This incurs massive overhead if you want to do copy on write versioning, because you might have to clone a 64 kilobyte page just to insert a 16-byte record or an 8-byte record. Instead, we use a write optimized variant of a B tree called the B epsilon tree. In a B epsilon tree, you make the tree a bit deeper, for example, twice as deep, and devote the space this frees up in internal nodes for buffering changes. So set index will just write to a change buffer in the root page, and when that root page buffer gets full, the buffer changes gradually spill down to the tree to the leaf pages in a way that minimizes dirty pages. Okay, so you're batching up your updates. This is a perfect fit for the MUTS discipline because it reduces the cost of versioning. It also a good fit for cloud storage because scattered updates are concentrated in a few pages that are cheap to send to cloud storage on AWS S3 or Azure Blob Storage. Implementing page data structures in Julia is quite painless. We use, again, the blob.jl package for page layouts. This lets us read a binary page from a global or local storage subsystem and interpret the page image as a blob contained in a Julia struct. Inside the struct, we find fields like tree height, number of records, and vectors containing change buffers and child page pointers. Blobs.jl defines custom getField and setField methods. So when we write node.height, that gets compiled into a dereference of a pointer to the height field in the page image. And when we need fast performance for queries, we can get raw pointers to vector data in the page and emit code that's very competitive with C and C++. Okay, if you want to learn a little bit more about this, check out Todd Green's talk at JuliaCon 2018, where he talks about low-level systems programming and high-level Julia. Last thing I'm going to talk about here, as in terms of sort of immutable data structures, is the pager. The pager helps us do automatic memory hierarchy management, where we don't have to worry if the data set that we're operating on is larger than the memory we have. It basically organizes data into pages and pages them in as they are needed. Unfortunately, historically, pagers have been implemented at a high cost in terms of the query performance, and that high cost exists even if the data fits in memory. And that sort of led to the creation of in-memory databases that don't have pagers and just basically load all the memory all the data into memory. Okay, some recent work by Thomas Neumann and his students has led to the development of new pagers that basically give us the best of both worlds. We get the out-of-core memory management, but we don't have to sacrifice in-memory performance when the data fits in memory. Okay. The page's role in a database is to manage its storage layers and transitions of data or pages between them. Like I just said, accessing data that is in memory is fast, but many machines have limited memory, so the pager also takes care of evicting pages from memory to make space for new ones. A good pager not only loads and evicts pages, but minimizes and balances latency cliffs. Traditionally, that might mean handling transitions between local storage and main memory gracefully. For a cloud-native database such as the one we're building at RelationalAI, it means overcoming the much larger latency gap between local storage, ESB, for example, on Amazon, and network round trips for cloud storage like S3. Implementing this capability was very straightforward in Julia. Julia lets us implement the pager design cleanly without any needless boilerplate. For example, the struct to the right holds all central data structures to implement the pager design depicted on the left. We manage the memory for the pages when we create, when we want to, and rely on Julia's garbage collection and other protections for the rest. This makes it easier to reason and debug about tricky code simply because there's just a lot less of it. Making the pager thread safe was straightforward thanks to lock defaults provided. By using a single lock, we can guard our in-memory structures and then convert our single-threaded pager to support task parallelism with only 2 additional words. For example, to commit multiple pages in parallel, we simply had to add the spawn macro. Easy peasy. And dropping down to a low-level interactions doesn't mean sacrificing the simplicity. As discussed earlier, we're using blobs.jl to manage access to raw pointers and to generate compact data layouts for our pages. In the code example to the left, we're allocating a new page pointer and add it to the page table, and it looks just like any other Julia type because it is. We also benefit from Julia's tooling for tuning and debugging, especially in this critical component. We all know Julia's interactive REPL environment, and we're benefiting from its code exploration macros, which we use to spot type instability and to find scary bugs like register corruption caused by latent LLVM bugs, which we all know exist. Our colleague Nathan Daly also wrote a Cthulhu, I can't pronounce it, .jl library, and we use it to interactively dive into the generated code. pprof.jl and memoryinspector.jl also help us profile and analyze the pager and optimize things further. Okay, the next component here that I'm not going to talk about is optimal join algorithms. I'm going to skip that, but sort of this is an algorithmic innovation that our team came up with. You can look at worst case optimal join algorithms. And then the final of the 5th component is a semantic query optimization or optimizer that takes a relational program as input and then produces an execution graph that optimizes the time and space that it takes to evaluate the relational program. Unfortunately, I don't have time to talk about that either, but it helps us just do amazing things, including optimize machine learning. Here's a quick example where we've converted a sort of a learning problem that traditionally requires that you build a data frame and send it to TensorFlow from taking something like 12,500 seconds to taking 18 seconds. And so the impact is enormous by emphasizing the brains part, which I'm not going to cover here today. So in closing, We think the relational paradigm is very important because it lets us separate the what from the how. And in so doing, we can automate a lot of tricky bits on behalf of people who use relational systems. I'll let you read this slide. And it's really a step towards the holy grail of automatic programming as described by Jim Gray in his Turing Award and is referenced here by Professor Don Vittori at the University of Texas, and talking about how the relational query optimization system is an example of, or a major advance towards automatic programming. Okay, and in conclusion, we built the world's first intelligent database, a knowledge graph management system that uses knowledge and data captured in enterprise databases to learn and reason. Please reach out if you have any interest in working with us or using the system that we built. We'd love to hear from you. Thank you very much.